Okay, solving graph problems. All right. So we're gonna look, like I said, we're gonna look at graphs and what it does today. It is um, very similar to a tree, and also very different at the same time. So we're gonna look at the similarities and some of the differences of what you can kind of expect from a graph. So if we look at a tree type of situation, we think of trees as having a parent node and then it has some children nodes. We think of like a let me see if I can do this. Share whiteboard. Haha. I finally have a whiteboard. Okay.
Oh,
So
I did.
I have a CEO, right? Okay. And then, I can think of this as a tree format. Underneath them is the VP of finance. And they're going to have underneath the CEO is going to be the CIO. And underneath the CEO is going to be other people, the VP of sales, and we can go on and on and on with all the people there. And underneath the CIO, you're going to have the IT director and the CTO, and on and on and on from there, right? So this is how we think of a normal tree type of structure. We have parent-child type relationships. The difference in a tree versus a graph is where you get these horrible people that come in and say, oh, but I need a dotted line boss. Okay. You ever seen a structure where you have like a dotted line boss? And like I report to this person, but there's this person way over here that I also report to. And I shouldn't have to, and I worked in one place. Everyone had two bosses. It was insane. It was the reason I didn't last there very long. I left. I was like, no, this is insanity. You should not have two bosses because two bosses mean that you have two different sets of like who they think what your priority should be. They want 100% of your time and 100% of
Yeah.
your focus, but you've only got like 50% to give them. So it was insane. So I left. I said that's stupid. So most of the time you don't see a lot of these dotted line things. Most people have figured out that that's stupid, and so we come in here and we go, no, make that go away. That's a tree structure. A graph structure is going to be a little bit different. And let's see if I can do this one more time. I'm going to draw shapes. As I have shapes, I've got some locations, and we can say that these are cities. We can say that these are anything we want. And then I'm going to have, look at that, I can draw. The thing that's a little bit different,
Yeah.
see if I can draw this, come on. Uh-huh.
Yes. You're doing it.
This is amazing.
I'm so proud.
Me too. Okay. The thing that makes this interesting is how do I connect from all these different places? Okay? Because I don't have a parent-child relationship. I can cross over. I can have where two people connect to me, or maybe even a third person connects to me. So I don't have a parent-child relationship. I've got just relationships between all these different nodes.
Yeah.
And so this is how a graph is set up. It's a little bit different. It's similar but different. Because it's going to be similar but different, they're going to do things like, this isn't a node. We're going to call it a vertice. And this relationship here, we're going to call this an edge. And where it becomes even more interesting is the fact that I can assign data to my edges. So I can say, for example, 84. And 84 is some value that I need to know about between these two vertices. Um, and I can say, well, this is a bigger one. This is 114, and I can think of these as uh, a distance in miles or a number of minutes or milliseconds to communicate, because these could be network nodes, these could be cities, and 114 minutes to get between two cities is okay. 114 minutes to get between two network nodes is not okay. So maybe that's milliseconds, or maybe it's miles or kilometers or whatever. But these edges can start to get values, and that gives my graph even more meaning, because now I can start to go, well, wait a second, if I have this type of meaning, then maybe I can start to figure out how to get from one point to another. And that becomes real important. That's a big part of what graph theory actually solves, is the idea, um, is the idea of how do I move from one location to another, from one vertex to another. The other things I get to start asking myself is like, can I only travel from vertex one to vertex two, but I can't go from two to one? So think of like a one-way street. If all of a sudden my vertices are intersections, and I need to be able to figure out how to travel through a city, knowing which ways I can go, excuse me, is real important. Excuse me, one quick. That's something that's really, really important. um, Years ago, and we're probably talking 20 years ago now, my grandfather got map software for his PC, and he thought it was awesome. And so he was going to use it to figure out how to get to my dad's place, see if there was a better route than the way he'd been taking for the last 15 years or something like that. And he plugged in, punched it all in, and that map software saw that there was an intersection between two edges, and assumed that, well, since there's an intersection where those two edges cross, then it told him to take it from there to there. It didn't realize that one of those edges over the other edge, there was no vertice there for a reason, because it was a bridge and there was no exit ramp. And so, he kind of joked, make a hard left turn and drop 15 feet onto that road. So, we have some interesting types of problems we have to be careful not to make assumptions about, and usually why we go from vertex to vertex, or from vertex to vertex, not from looking at where edges necessarily might cross, because we don't know why there's not a crossing there. We can't make assumptions. Um, so that's kind of the idea. The good news is that if you look at how to solve this problem, we looked before spring break at depth first searching. That's usually how we're going to solve these problems. Is we're going to use some sort of depth first searching, often with some sort of heuristical type of model. Usually it's going to be in a greedy format. And what that means is I'm going to go in and say I need to find a way to get from point A to point B. And when I'm getting from point A to point B, I'm going to look at one set of nodes, and then I'll look at another and see if I can get a good enough route that way. So I'm going to follow this set until I either find that I can't get there, or that I've gotten there and I've made my time, and that's good. And so I divide and conquer until I get my answer that I'm looking for. And I'm constantly going to be looking for, well, what's my next shortest road that I can take? So I go down this road, and I go, and I only have to go 500 feet. Well, that's a lot short. My next one's 6 miles. 500 feet is a whole lot short. Let me take this one, because maybe this one, just little bits, and I can start to think about how I'm going to get my best option. And they call that a greedy uh, algorithm. Maybe I look at where that endpoint's going to be and say, well, that's going to get me physically closer, and so it's like I can find distance between two vertices, straight line, and so I'm gonna do that. Um, if I start having to test every possible combination, though, this becomes a brute force answer. Um, and that's kind of worst case scenario, but that does happen, a brute force result. And that becomes really problematic because this is a infactorial problem. So remember we talked about Big O? And we talked about how efficient an algorithm winds up being. If we're not careful, Big O on this becomes infactorial. Um, so adding a few new nodes becomes just amazingly complex. So we have to find smart ways of how to solve this so we don't get into a worst case scenario. Because if we think of as a vertice as every possible street combination where we have an intersection and I need to figure out how to get across town or get someplace 2 towns over, how many of those intersections do I wind up running into? Way too many. So we're going to look at a couple different things with that so we can make some good decisions on how to pick those. So let's look at 2 common problems that we see. And the first one's one that I saw, probably the first one that I saw as far as a graph type problem. And that was known as a traveling salesperson. So the idea came out of, and this was actually a real world problem, of there was a company that needed to send a person out to go visit a series of cities. And they said, we want to find the most efficient route for him to go on his sales path. We want him to therefore be able to determine what's the best way for him to go from city to city to city. And so this became known as a traveling salesman problem. It's been updated to now be a traveling salesperson problem. And this is a problem that lots and lots of companies have. And each one's going to throw their own little twist on it. I want to visit every city, but I only can visit a city once. So I can't hit a vertice twice. Or I've got certain, I have to be in certain places at certain times. But the others I need to hit efficiently. Because maybe they're having a hit for a trade show or conference or something like that. There's lots of little variables that can be thrown in here that make this really, really complicated. There's a form of this that UPS solved a couple years back and looking to be more efficient, and they wanted to hit all of their locations but only make right-hand turns. And so when they loaded up their path for their truck to follow, they gave them a path that would only make them have to take right-hand turns, because since you can turn on a red light on a red, the idea was, well, this is going to be a lot more efficient for us long term. So it might be a little bit more efficient from going A to B, but when I consider A through double Z, because I've got so many other options, it's going to be more efficient. And so there's lots of little twists on this. We're just going to look at really simple and say, we're driving, we're only looking at straight distances, we're assuming speed limits are the same, all that type of stuff. So if we start to look at the graph and start to look at all those edges and vertices, we realize that things start to look like a map structure. And we can figure out that information between those. We're going to make the assumption that we're only going to go between places that have highways connecting them. And that's not an uncommon problem in reality. If you look, certain companies, they are notorious for doing stuff like that. We mentioned UPS with their right-hand turns, but like Walmart and Sam's, they're owned by the same company. They make sure that Walmart's might be standalone, but Sam's are always next to a Walmart. The worst you might get is have to cross over an intersection. But they're going to be on the same side of the road They're not going to be catty corner, so that their trucks can move in. There's a couple places I've seen where they actually share the same parking lot. Um, Costco's another one that's notorious. They only put stuff within so many miles of an interstate. Same thing with Cracker Barrel. I've never seen a Cracker Barrel that's not by an interstate exit. Um, I'm not saying that there's not. I've never seen one. Um, they always want to keep those things really close because they're looking at simplifying these problem, and this is actually the problem that they're working on solving. Um, so here's an example of what you might see. Um, we got to start and stop at the same point. Where are we going to start and stop, and how are we going to get from place to place? If I start at school, I could go to the gym, which is 10 miles away, or the movies are 10 miles away. Well, how does that affect me as I kind of move through my whole system? That becomes a real challenge. Like if I went to movies because I wanted to go that way, and then I could go to Snell's Farm. Well, that's only 7. That's shorter than the 10 to 15 of going to the gym and then the movies. So I start to think, oh, this is a better route. But as I progress forward, I have to ask myself, is it really, or was there another problem with that and reason why they
Correct me if I'm
picked?
wrong, but we're basically just doing like it's like Google Maps
Well,
essentially. You already make that comment, and I missed it somehow.
so I haven't made that direct comment, and that becomes a really interesting problem. That becomes actually a more complicated version of this problem.
Oh no, I meant like on like a very not like
Yes.
that. It's like on an extremely surface level, very like
Mhm.
just like it just find most efficient route.
Exactly. That's exactly what it's like. And we're actually going to look at next thing we're going to look at is going to be uh, like Google Maps, and we're going to see how. And the great problem with Google Maps is my wife loves to use MapQuest. She still uses MapQuest after all these years. And then she'll like look it up in Google Maps and go, "How come it gave me a different route?" And we'll talk about why it does that in just a few minutes. But there's more than one way to hit all those points, and so it becomes a how do I find the best way, and what's the best way? Maybe the best way is because I've got to hit a 3 p.m. movie, and that's what I really care about, and so I'm just putting everything else around to make it work. So
Mm-hmm.
it becomes an interesting thing as you're working through this process. And generally what happens is you're going to say, okay, I'm going to try to go here, then I'm going to try to go here, and I'm going to calculate that. And then I'm going to find, can I find another option? And if I find an option that takes longer than what I've got as my best option, stop checking it, back up, start over. Let's do another one. And how do I work that problem? It becomes a real interesting problem. I'm actually trying to find algorithmically is easy to describe. Programmatically, it's a little bit of a challenge because you have to keep track of what nodes have you visited, um, what's the best route, am I allowed to go through a node twice? Uh, because maybe that's the best way. Maybe it's the only way. If I start off with something where I can go 3 ways one way, but I've got to go down this little kind of trail that doesn't allow me to backtrack. So it's an interesting problem and how to solve, and knowing all the nuances of that problem allow us to be able to solve it better. But even at a real high level with no nuances, it becomes kind of an interesting situation because of all stuff we have to track. The other thing that becomes, I'll talk about that one in a second. As
Maybe
we,
I'm like overthinking this one part, but like, why would you ever, if you're trying to get from one spot to another,
mm-hmm.
why would you ever need to hit the same node like twice? Because if you come back, like that doesn't make any sense.
Okay, so
Or,
let's.
or, or if I'm overthinking that, and we can just come back to that on a different day completely. But I guess just try to like show you like let's say like my mental picture, right?
Okay,
So you have kind of like
Let's see if we can.
Actually, no, I don't even know how to, unless I have like a board, I can't draw anything or try to.
Come on, be big. No, no, that's not what I want. I just want to view this image. Okay, so let's talk about an example why you might want to have a place where you hit multiple times. Let me see if I can annotate. Okay, so let's say I'm going to start in Chicago. You cannot see that. Let's pick a color we can. Okay, let's say we're going to start in Chicago.
Mm-hmm.
And then I'm going to come over here to New York City. Okay, that's pretty straightforward, right?
Yeah.
Then you need to go to Boston. This is going to end in 10 minutes. Okay. Okay, stop annotating so I can click the OK button. All right, there we go. All right. And I'm also going to need to head down to DC, Charlotte, Atlanta, Kansas City, let's say. Okay.
Okay,
Now,
I see what you're doing now. Like where what I was thinking, like
yeah,
at the
I mean,
time, was like say if I'm just going from Chicago to Boston, I was thinking, okay, well, you fly from Chicago to New York to Baltimore to back to New York to Boston, but because you hit New York City twice.
right.
But I wasn't thinking about you got to go from Chicago to Boston. Maybe you got to go through New York City, then to go from Boston to Charlotte, you got to hit New York City again.
Yeah, exactly.
So it's different trips.
So
Or well, no, same trip, but you got to hit a bunch of different locations.
I got to hit a bunch of different locations, and I don't want to go through a city any more than I have to.
Yeah.
But I may, the only way to maybe get to Boston is to go through New York City, which means, and I can't go to Boston to any place else. I got to go back to New York City. And so that's one of those problems I have to look at. Like, okay, I hit this node. Is it okay to hit it again? Maybe. And that's where it becomes a real problem. Because otherwise, if I'm not careful, I can start to get in like this circular loop where I go Chicago to New York City to Boston, Boston to New York City. Let's go back to Boston. And I get like, because this is my shortest node, now I just jump back and forth between these two. And I don't want to do that. Excuse me. Oh, sorry. I don't want to do that. I want to be mindful of how I'm hitting my nodes and being careful. So that's where you start running into some of these issues. Let me switch back to my mouse. Close that. Yay for the internet to be able to handle stuff like that. Oh, it's still showing all my annotations. Wait, can you guys see my annotations on the screen, or is it just me?
Yeah, I can see
yeah.
Really? Okay. Clear all. Oh, there we go. Clear all drawings. Whew. So, that's some of the problems we have to try to figure out is how do we handle, because you're right, I don't want to repeat hitting something if I can avoid it just because it's faster in the short term. If I think about like a spoken hub type of situation where I have a situation in the center and I want to go out here and I can come back and I can go from the center out there and go back. Well, it'd be easier just to go out and then go around, because that round trip of going back and forth is going to be real time consuming. So I have to be mindful of those types of problems. And that's the reason why that graph problem can get really big and be that n factorial. So if you've not, let's see here, pull up my calculator app. I got to switch over to scientific. Yeah. So, if I had 9 cities, 9 factorial means that there's 362,000 possible combinations. And that's just if I had 9 cities to possibly hit. If I had, like my father-in-law, he used to be a salesperson before he retired, and he might go and spend 6 weeks kind of traveling, going up and down the seaboard, doing a bunch of different stuff. Let's say he had 25 places he had to hit. 25 factorial, you just wanted a little bit over double. Let's hear it's hundreds, thousands, millions, billions, trillions. What's after trillions? Because there's 3 more commas. Uh,
there's like quintillion something.
yeah, I can't remember what it is after quintillions. And you still have 2 more comma sets. I mean, it's just a ridiculous number when you start, and that's with only 25 stops. And you don't want to spend, you don't want to calculate every one of those. So at some point, and this becomes a bigger issue with like your Google Maps and stuff like that, is one of the things you have to actually look at and think about is when you become good enough. Okay, we got a result. This works. This is something I can work with. Let's just send it out there. Because I can't still process this for another 15 years to find the best route. This is a good enough model. So that's something we have to look at. Is this is a very potentially inefficient solution, unless, like I said, this is a really, really big subset of computer science, and you can spend a whole semester on it. We're spending a week. So there are ways to optimize graphs and fold things down and do some interesting stuff with them. And this winds up getting used in artificial intelligence. Everything from if you're playing, a first-person shooter game, the players have to know, the non-player characters, they have to know, how do I go from point A to point B? And if you set them free, they got to know and be able to figure it out. So there's a lot of different things that happen, whether you're doing a maze game or a first-person shooter, or you're doing any of those things where artificial intelligence is coming in place. I think I want to talk about the GPS version next class, just so we can kind of talk about that in a little bit more detail and whatnot, and all the problems and features that get put into that. So it's a real interesting subset if that's what interests you. There's a whole bunch that you can learn, and I can give you some ideas and resources to let you dig deeper. But this kind of just gives you that overview of what that traveling salesperson problem is and what graph theories and sets of problems can be. Okay. Any questions on that? All right. Do you guys just want to go ahead and call this a day, and then we'll do the GPS one next class? Does that work for everyone?
Yeah.
Okay. All right, let's go ahead and do that. We'll go ahead and disconnect because we're going to get disconnected in about 2 minutes anyways. We can rejoin the meeting though. Kate and Denise, I know there's a couple things I want to talk to you about with the other class. So if you guys want to do that, Tyson, you don't need to be here for that, so you can go have lunch. Oh, are you on campus?
Me?
Yeah.
Yes, I am.
Do you know if the Chick-fil-A is open or if it's just
Chick-fil-A is open
for in dining, so you can eat in there? Awesome.
Yeah, you can eat in there.
Okay.
In there before this class.
Yes. All right. My 21-year-old son who's autistic, that's where he wants to go for his birthday dinner tonight. And not being able to go would have been a really big problem.
Yeah.
So, yeah,
because still open.
He's 21 and he's big, and he lets you know when he's not happy. So, all right, awesome.
Okay.
All right, I will see you all on Thursday, and Kate and Denise I'll see you guys in just 2 minutes. Does that sound good?
Yeah.
All right.
Thanks, all. Take care, everyone. I'll see you all later.
All right.